Swayam Prabha, free DTH channel for education.
Okay, let me share the screen here, and let me go to begin with the write up here. So if you recollect in the last, let me put it in where, everywhere it is a okay. Okay, maybe I wish. Uh, I'm just trying to. Okay, this is better. Fine. Right. So, in the last Zoom session, we were discussing about the cosine function, right? We were looking into the behavior of this cosine function in the last session, right? And then what we have arrived at in that discussion is this can this will be oriented when you have cos 2 pi of k naught into x plus k1 into y. This will be oriented at a particular direction when your both k naught and k1 are non-zero, right? So that's what this orientation we figured out for it. This would be equal to tan inverse of k1 by k naught. And then we also figured out what would be the periodicity of this function in that particular orientation. So that turned out to be 1 by square root of k naught square plus k1 square. Is everyone fine with this? Is my fan causing any noise? Otherwise, I'll switch it off. No, is my audio clear?
Yes, sir.
Okay, fine. Then I'll keep it. Okay, so hope everybody is clear so far, right? So then what we have done is we started with taking on the spatial domain this function and trying to figure out what would be its frequency domain response, or what is its f of kx comma ky. That's what we did in the recorded video lecture. So what happened there? F of xy is equal to half of this. Anyway, first we are writing this, representing this in terms of the complex exponentials, right? And then we already know that for one it is delta here, delta of kx comma ky. Since we are multiplying it with complex exponential on the spatial domain, right, that would result in shifting in the frequency domain. So since it is there will be anyway sign change will be there. So 2j times 2 pi of k naught x plus k1 y would be equal to delta of kx minus k naught and ky minus k1. Similarly, this part also has been written here, and this is what you have arrived at, right? So that would be the frequency domain response. Now, if you now consider the, yeah, this is better. So if you now try assume that this k naught and k1 are positive, this is how the Fourier domain frequency domain response would look like. One point at k0 k1 and another value, its value is in fact 1 by 2 there because this multiplication factor is there, that is equal to minus k naught minus k1. So if you this becomes, so once you have, in other words, you have a cosine on the spatial domain. Look here, these are the values of this Fourier transform. So in these limits, if you just try to take a look at here, since here there is a the better way to get an intuition for it is you substitute in place of f of kx comma ky what you got there. Then what's going to happen? it's going to have values at k naught, k1, minus k naught, minus k1. Only at these 2 points it has values, right? So in that case, you take a look at here, and that value is 1 by 2 there, is it not? Because that multiplication factor is there. So if you substitute here, you would see that this would be equal to 1 by 2 times e power j 2 pi into k naught x plus k1 by plus e power minus j times 2 pi of k naught x plus k1y. So that would give you 2 times cos, that half and half gets cancelled. So essentially, since you have cosine, you are linear combinations of sines and cosines. If you look at it, e power j 2 pi kx ky, this is what you have. Whereas here you have a particular value for particular values of kx and ky, you have that f of xy is there in the particular example we have taken. So you essentially need to get rid of this function. That's why its value is there at k naught and minus k naught, so that e power j 2 pi and e power minus j 2 pi, this is getting cancelled. This is getting multiplied by twice. So that's what is giving you the half there, right? So essentially a given signal, the basis functions when you are going to the Fourier domain are sines and cosines. But since both sine and cosine are here, you would be getting 2 points in a way that you would get rid of the sine and you are just left with cosine, and of course some multiplication factor during this summation. Is this clear? Is this example clear? And then interpretation for the result that you are getting, is that clear? Are any questions here? No. Yeah. No questions. Okay. So then what else? uh, yeah, that's the very reason why from here also you could see why when you have a real signal, you have a complex conjugate response. It's because when you are integrating over the entire region, you should not be having any imaginary part here, because on the left, finally at the end of your whole integration, you should be simply getting a real number there, is it not? So that's the reason why once you, at whatever response you have kx, if it is a plus jb minus kx or k naught you call it, assume k naught being positive, okay, or you should be calling it as k naught k1 in fact, because this being 2D. Okay, there if you have a plus jb, same minus k naught minus k1, you would be, when f of xy is real, you would be having a minus jb, so that when you are summing up the whole thing, you are simply left with the real part. And a similar interpretation you could do when your f of xy is going to be imaginary part. A similar explanation you could come up with there. Hope everybody is fine with this interpretation. And then ignore about f of xy being cosine. You take any function. So the kind of interpretation that you could have here is, we have already, let me now go to the slides. Oh, 1 minute. Okay. Right. So now, as I'm just since I'm not going in a sequential manner here, because anyway you guys have done it. See, this is how you could make sense of what's going on in case of images, two-dimensional case, the Fourier transform stuff. Suppose if you have only assume that ky is, you are varying both kx and ky. Okay, now you anyway at the end of the day, although we are doing right now, so what would happen in practice actually when it comes to images? What happens to your left hand side in the earlier uh, this expression? Let's start with this expression. So what would happen to the left hand side here when it comes to an image? In fact, no, so what happens to the nature of this function when there is an image?
It's
Hello.
discrete.
Sorry, yes, discrete. So how do you get it now that you have done, many of you have seen it multiple times, you could answer these sequence of questions now. How do you make it discrete? We will anyway see it later in the next couple of classes in more detail, but I would like you to answer these questions. How do you make it discrete, for example? Mathematically, what is the way you could think of making it
By
discrete?
sampling.
Yes, by sampling means what exactly will you do there mathematically?
We take intervals of
Hmm.
if it's
So yeah,
discrete,
like with which function, for example, doing some operation with a given this function should give you that. So what is that? I want to.
Two-dimensional
Hmm?
sampling function.
Sorry.
Two-dimensional impulse train.
Right. Correct. Two-dimensional impulse train. Now that you have mentioned that, I would like you also to visualize how does it look like. How do you? What do you think it would look like?
a bed of needles.
Right. Exactly. It looks like a bed of nails. Hmm. So you have on the grid, at every grid point of xy, okay, you have those points. So that's what you are going to multiply here, is it not? To get only, retain only the samples at regular intervals. And of course, after that, what's the next operation you would be doing in order to make it discrete? You normalize your x-axis with some, if your sampling time is ts, you just simply do ts, that is equivalent to having n varying from minus infinity to plus infinity. Is that fine? Now what is now multiplication with a bed of nails here? Okay, it's fine even if we talk in terms of 1D here. Okay, so now multiplication, what is the effect? Its effect is going to be on the frequency domain. Now I have a.
Aliasing could happen.
Sorry,
Aliasing could happen.
should it happen all the time?
No, not necessarily.
Yeah, yeah. So you tell me in terms of the mathematical function, what is going to happen there? The moment you
Convolution with
are right. So see, let me put it maybe more specifically. I have a particular frequency spectrum here. Okay, I also assume it is a band limited one. Okay. Now the moment I am multiplying it with impulse train, what would happen to the frequency domain response? The moment I am multiplying on the spatial domain with an impulse train, so that I have only some samples of it, and what would happen to the earlier frequency spectrum of the continuous time function?
it will get repeated after
That's
some
right.
intervals.
You get multiple copies of it, and the placement is dependent on.
Sampling period
Sampling
of the
frequency.
sampling function.
That's right, on sampling frequency. So if I give you sampling frequency, can let's say I say that I'm sampling with a rate of ts, okay, t subscript s. Can you tell where the copies would be placed? Or well, let me also take omega s is the corresponding sampling frequency. Okay, 2 pi by t would give me the sampling frequency, right?
At
So
omega is 2 omega is
right,
then
exactly. So you have repeated copies of it placed at an interval of omega s in all the places. That's what is happening. So that's the effect of having a discrete time image here. Then what is the next thing we have to do? We are forced to do in a way other than sampling here. When it comes to the implementation, but so now
Sir,
yeah.
sir, we can have two frequencies, right? Like it is obviously a bed of needles. Like in X direction, we will have one frequency, and in Y direction, we can have one
Yeah.
frequency.
See, it would be
So
a rectangular grid, but still it's a bed of needles, except
yes,
that
sir.
your spacing is different.
So omega s is the frequency in, like,
Yeah.
did you assume omega is in both directions same?
Yeah. Anyway, I was telling it in case of 1D, but then you could have two different frequencies in both. So aliasing could come either in X direction or in Y direction. So here, that's a good point to again emphasize. Now you are going to, we will anyway do it formally in the next video lecture. But again, before that, it is not at all difficult for you to visualize what's going to happen. Now you not only keep copies along the X axis, but you are going to, since now the impulse functions that you have is a bed of nails. Okay, a rectangular grid everywhere you have. So wherever there is an impulse, you are going to keep a copy there on the frequency. Of course, that 1 by omega, the spacing of impulses. So wherever that rectangular grid is there, everywhere you would be keeping a copy there. So the aliasing could occur either from the top, bottom, left, and right now.
We will pass it through average filter,
Which one?
through averaging filter,
No, why? For
smoothing
what?
filter to avoid aliasing.
Yeah, no, smoothing filter. Yes, better we call it as a low pass filter. It could be smoothing or anything. Essentially, you want to cut its wings beyond a particular length. So you could call it as a band, like a low pass filter. You usually keep only low frequencies and make the rest to zero. Fine. Of course,
Yes, yes.
smoothing filter is also a low pass filter. That's one type of low pass filter. That's all I am saying. Because the moment you are applying smoothing, anyway, you will get rid of the frequencies. Gaussian, for example, you take frequency domain response, that's again a Gaussian. So you would get rid of the higher order frequencies, right? Okay, now can we, so what would be the one quick question here? Then what would be the impact of again discretizing there? What is the other impact on the frequency domain that's going to happen? See, one thing is copies are placed, that is fine. But when it comes to this integration, do you see something going to happen there to the frequency domain response? See, one thing we thought about is you are discretizing it. So that's equivalent to multiplying with a train of impulses. Okay, that made your keeping multiple copies of it. Is that all? Now, suppose if you are going to, what happens to the Fourier transform of that discrete time signal now? Look at, start from here. Okay, now I want to make it transform, okay, morph into the Fourier transform for this discrete time signal. So what's going to additional thing I have to change here, make changes here?
Summation.
Hmm?
Summation in place of
Yeah,
integral.
summation. Not
You have to
really.
make it into DFT, sir.
No, DFT, we are going, we still have few more steps before we
So
come
it will
there.
be it will
Yeah,
be periodic from minus pi to pi.
very good. That's the important point. See, summation will come here in the second expression of f of xy. You get summation here. Okay, here this we have, still we haven't talked anything about the frequency. Correct. So the first impact of it here would be, you would see this frequency spectrum being periodic, that you have already said that there are multiple copies of it placed. That means in terms of equation, it is becoming periodic. Correct. So how do you deal that? How could you see that out? Because here this x and y here, these are going to be integers. So j times 2 pi times kx into x. Now beyond values of minus pi to pi, this is going to get repeated. So to deal with it more efficiently, you would be modifying the limits of it. We will see the equations anyway a little later, but intuition is more important. So the first casualty of converting that here is the limits would now change from instead of minus infinity to plus infinity over a period of 2 pi. That's good enough. Okay. And the other one, as one of you is mentioning, summation part would come here. So here the limits would be changing here, or which you are be integrating. Here this f of xy, let's call it as now f of maybe n1 comma n2. I'll put the exact notations as we move on, but something like that. That effect would be this being discrete. These integrals will convert into summations, right? Now again, you can't have, you can't store every frequency, right? You could only, particularly if you want to do something with the computer, you cannot do handle with all frequencies at once. So how do you discretize frequencies now? What's the way you could discretize frequencies? You can store only discrete values of frequencies. Now I give you this second expression. Okay, And I want you to get out of this f of kx comma ky, I would like you to retain only some certain frequencies. So what would you do now?
Multiply with again a bed of nails.
Multiply it with.
Again the same bed of nails.
That's very
Starting
good.
of
That's right. That's right. You simply multiply this one with again an impulse function. So again, see it in the 1D for simplicity. So the moment you are multiplying here with impulse train, what would happen? On the spatial domain now, what is the its effect? The moment you are storing on the frequency domain only limited samples,
we
what
get
is it?
copies of it in repeated copies of
That's right. So it is equivalent to what applying what function on f of xy now? What transformation you are going to do to f of xy now the moment I am discretizing here?
convolution with impulse train.
Right, convolution with the impulse train. So you are going to place multiple copies of it now. So again, is there any chance of aliasing now if you are doing it?
Yes,
And you
sir.
are, yes. So this aliasing we refer to as
Time domain aliasing.
time domain aliasing. Right, earlier one was aliasing the moment you are taking samples in the spatial domain on the frequency domain, and if your unless your sampling is good enough and unless your signal is band limited, you could have aliasing on the frequency domain. And now anyway you cannot live with having a continuous frequency, because at the end of the day once you go to Fourier domain and then you need to come back. So while you are coming back, your calculations and everything, you could only have a set of values. So in order to do that, what you have to do here is, once you are keeping only few discrete values of it, so that means it's equivalent to mathematically multiplying it with an impulse train. So that's equivalent to, if you right away take now the inverse Fourier transform of it, then what would happen on the other side? This multiplication here is equivalent to convolution of f of xy. Okay, for the time being assume f of xy is continuous, doesn't really matter, or the same thing is applicable even when it is discrete. We could already, since we made it discretized, assume that you already have a discretized function there. Then these copies are placed now. Again in 2D, again the aliasing could come from either of the x, y, or that means the copies are placed left and right in case of 1D, now top and bottom also in case of 2D. So from any of these two places the aliasing could come, unless you are taking enough samples of it. Okay, that's finally when you are taking both the samples, your original signal, just like the moment you are taking samples from f of xy and going there, you are assuming that the signal is band limited, and unless and otherwise the signal is band limited, you won't be having enough samples, right? If it is of course there are a few other exceptions which I don't want to go now. Suppose if your signal is going on and there are no limits to it, then you can't decide on which frequency, which sampling rate to figure out, so that there is no aliasing. Okay, so that's why you might, even if the signal's nature is not band pass, you would apply a low pass filtering, you make it band pass, and then you do it. So in order to avoid aliasing there, one constraint you are putting there is uh, assuming that you are making your signal a band limited signal. So what is the assumption on this side actually when you are moving from frequency domain to the spatial domain? Is there any assumption there that we need to take into that the signal should satisfy such that you would be getting back, you will be able to recover your signal back?
There was no aliasing in the frequency domain.
See, that you forget about. Now I'm not talking about, I'm going one way now. I reached already Fourier domain. Now I'm from the Fourier domain. I cannot afford to have a continuous values of the Fourier domain because I want to do things in a computer. So I want to take samples of it. Okay. So what is that in order to appropriately get back? See, you can already see that the copies are placed both in x and y directions, both negative and positive values of x and y at regular intervals it is placed. So I want to recover back my f of xy from the resulting inverse Fourier transform. So what is it that now f of xy should satisfy now, so that I'll be able to recover back my signal?
Sir, while multiplying with like bed of nails, the frequency should be more than two, like frequency should be 2 pi. So that to avoid aliasing.
Yeah, you are still beating around the bush. It's not the right answer. See, I already mentioned in the while saying about moving from f of xy to its Fourier domain, we are assuming that the signal is band limited. Okay, should I make any similar assumption here, or similar constraint I need to impose here in order to get back my signal? That's the question.
Signal should be time limited, then so or periodic, I think.
Hmm?
The signal should be periodic in spatial domain.
No, that's not the one. See, issue is there any? See, when
I
I am
think it should be
moving from
band
f of
limited.
x, yeah.
I think it should be band limited even in frequency domain.
What do you mean by band limited in the spatial domain? It's about frequencies we call.
No, in frequency domain.
That's okay. I'm given an f of x, kx comma ky now. Okay, I want to get back now.
The sampling frequency should be at least twice the bandwidth of the frequency domain.
No. See, talk in terms of now f of xy. See, when I am moving from f of xy to the frequency domain, I said that the frequencies of it, if I want to discretize here and still get back my signal, the constraint I posed is that this frequency should be band limited. Okay. Now I am asking you the inverse. I am moving from frequency domain to the spatial domain. What is it that you want to get back your signal?
F of xy should be finite duration signal.
Right, very good. That's all. Unless your f of xy is finite duration, okay? So all these concepts, why should it be finite duration now?
To prevent the time domain aliasing.
That's right. So unless you know what is the length of the signal, okay. Otherwise, what would happen if I am keeping a copy? This is there, for example, from -10 to +10, okay. And now I am keeping next copy at 5 itself, okay. You could figure out in similar lines where the next copy would come. So there is an aliasing happening there. So to avoid that, just like the signal has to be band limited there, the moment you are discretizing your frequency, how you discretize it would depend on the first condition is your signal should be there, it is band limited, here it is finite. And should we also know the length of that signal? Should I know, okay, that's fine, I know that this is a finite length signal, but should I also know what is the length of that finite signal to recover back when I move from frequency domain to the spatial domain? Is the question clear? I want to move from the frequency domain to the spatial domain. One point that has been mentioned is your f of xy should be, or f of, don't now call it as let's say a discrete time signal, okay. F of m comma n should be a finite length signal. So the next question is, should you know the length or not, so that you would be able to later recover back? It's a finite length, I tell you. Is that good enough? Should I tell you the length also?
Yes, sir. To integrate it, we need its
Unless you
maximum.
know the length, you don't know with what rate you should take the samples here for the frequency spectrum. Is it not? You are going to take again samples of this frequency spectrum and storing it, just like you are taking it in order to know how many samples of this continuous function you should take. For that, you should know the frequency here, because from that you know where these copies are placed, right? Here also, it's not only finite length. You should also know what is the length. Okay. Now, suppose if I give you the length n, okay, capital N, then only you would be able to say how many samples are required here. Is everyone able to follow this? This is a kind of the whole summary of the sampling. Okay, we start with continuous time. You sample on the continuous time domain. What is it that you are getting in the frequency domain? Then from the frequency domain, now you are taking samples of it. Then what is the impact of it? In fact, by the time we initially start with both being continuous, that is continuous time Fourier transform, you make this discrete, then what you are getting is DTFT, then you are making this also discrete, that is what giving you DFT. So all transforms are part of this just simple pipeline that we have seen now. Anyway, sampling, I would like to spend a couple of classes on that, just to one more time it would act as a like a refresher for you, where something which we discussed, or maybe 10 classes would be discussing around 2 classes, so that in a way is good, you get the whole summary and gist of it. Okay, the same thing when we are introducing them to you for the first time would be discussing around 10 classes, but I hope now you got the big picture of it clearly, right? Any questions so far?
Sir, can you just say why we need the lengths of the signal?
Why we right, good. So see, yeah, I am trying to write it without I'm trying to explain it without writing into equations, so that part try to get an intuition now here. See, the moment you are taking samples here, what is it equivalent to? See, I cannot store the whole frequency here. Okay, so I'm taking samples of it, correct? So samples is equivalent to multiplying with an impulse train, correct?
Hmm.
On the frequency, multiplying this with an impulse train would give me the samples of it, resulting one. So far fine.
Yes, sir.
So that is equivalent to convolving whatever is there on the
The time
spatial domain with convolution, correct? Convolving it with the impulse train, is it
Yes,
not?
sir. Yes,
So
sir.
the moment I am convolving with impulse train, what it will do, it will keep copies of it, right?
Yes, sir. Yes, sir.
When will I be able to recover my signal? When I am keeping these copies, the values should not be overlapping.
Hmm. That is the
So
aliasing should not.
exactly. So so unless I know what is this length of the signal, so 2 pi by n, based on that, you would be doing the number of samples you take here. If your signal is of length n, unless you take samples at which are you should take n samples here also. Look at now, since you DFT, you already know, if you have n samples, if your finite length is capital N, your number of samples you should take from frequency are also capital N.
Should be n.
No? So if that is not the case, what would happen? For any small value, then they accordingly, how much overlap is there, accordingly so many values gets corrupted. There is no way you could recover them back.
Okay, sir.
Is that clear?
Yes, sir.
Yeah, make use of this discussion that we would be having in this, and also next few classes, because that could be helpful for you for your interviews and other things also, when DSP comes into picture. So these are all the concepts that have to be very clear, okay, in the sampling particularly. Any other questions? Don't hesitate to ask if you have any other queries here. Is everyone else following this? No one have? Yeah, I would like to hear something from MTech students also. Like, is everybody? Are you in line? Are you in the same pace? Are you able to follow that? Harshavardhan,
Yes, sir.
is it clear? Is the
Yes,
discussion
sir. Yes,
clear,
sir.
or is it too much?
No, sir. Clear, sir.
It's clear, right? Good.
Something like this.
Yeah. So we could afford some time here if you have any questions of what we discussed. Again, I'm not going into the math part at this point itself. That anyway we will serve that need a little later in the next few classes. But the overall picture should be clear on what exactly is happening. Okay, fine. So actually, even in the presentation, that if you had seen the images and all here, we were in fact already assuming that this is the DFT that we are talking about. It's not really the moment you are programming and plotting certain things, it has to be DFT only. It cannot be DTFT. It cannot be CTFT also, right? So although we have not formally discussed any of these things, we were already in fact the moment see basically this is only discrete time only, because you have to store it in an array and do it. So this was not in fact CTFT. The moment you are plotting, that's DTFT. And then in the frequency domain also, you cannot plot everything and then you want to come back. For example, in the examples that I have given you, okay, like here, okay, this example, if you had already seen it, that means already we are talking about only DFT, not in fact CTFT. Hope all of you had realized that while going through it. If not, I hope at least this point is clear right now. Okay, anyway, we will come little more organized here from the beginning and finish it off. Okay, so you should be able to, by looking at the images, I'm sure you will be able to say whether it is a high frequency or low frequency, right? See, the way it is getting repeated is fast here, right? So that means this is a high frequency thing, isn't it? Hope everybody looking at the image, if somebody is not able to say it's high frequency or low frequency, be comfortable with it. Okay, and then also be clear that the whole sinusoidal variation would be just in this small region. It's not like the whole sinusoid is in this way going out. That also is something people would confuse. Okay, the whole sinusoid, one cycle is there just within one band here. Okay, it's not the entire image. Hope that point is also clear to everyone. Okay, so this is high frequency one, correct? And another point should be also clear by this time is this orientation of this. Okay, this orientation of your frequency domain response would be same as the orientation in which your cosine or sine is there, right? So that's why you could tell in which direction it is. And in terms of magnitudes, if your kx and ky are increasing, you could see here the expressions you have at k0, sorry, k0 and k1 are increasing, let's say, then this would also increase. This will go farther. So if I give you like this, for example, orientation is here. Hope it writes here. Yeah, you could see the orientation is in this direction here, right? So your e power j and e power minus j should be here. Okay, now this orientation has changed in this direction now, so they also should be in the same direction here. And then another thing you could say is frequency relatively is it more or less here compared to the next slide?
Less.
Yes, it is less. So it is increasing, frequency is increasing. So these points would also go away from the origin. Okay, that's more clear when you see just these two images. It would go farther and farther here. As you could see here, they moved away here. Okay, they moved to here. So that interpretation should be very clear to you. Okay. Uh, are you fine now with uh, correlating what we have seen in terms of equations of cosine and sine? So if you plot it, this is how it would look like. Say here, this is your x-axis, this is your y-axis. Okay, this is where it is changing. And notice that this is for, let's say here, this is one period of your signal. Okay, that's what it is happening here. Okay, so here, this is one. So yeah, that's what is happening here. Okay, if I just draw it there, then that's how it is varying. Right, so then if you look at here, let's say the way whole variation, okay, if you look at here, is within that itself it is varying. If I just plot it, so every repeated pattern in that direction, the frequency is high there. Is everyone fine with cosines and sines, both k0 and k1 being non-zero? Hope you are able to make a clear interpretation of that. Or any question there? Okay, right. So this is the example where the earlier example in the previous class was a box function where your x minus 1 by 2 to plus 1 by 2, y -1/2 to +1/2, you have a function, but then you have this a symmetric function, but the limits need not be simply 1/2 and -1/2. You could have different values of x. Okay, this derivation also you please try yourself. I could ask you something like this in exam. Okay, and then as I was mentioning earlier, you should be comfortable drawing any sinc function, not just sinc of x 1 2 3 4, okay, where it is 0, but any sinc function also you be comfortable in drawing that, right? So that would be now sinc, that's multiplication of them, and then capital X capital Y, these are not don't mistake it with varying values. It's just -x/2 to +x/2. So for example, compared to box function, this would be x and y would be 1 here. Okay, in the box function, if you want, you substitute x equal to y equal to 1. So then you could see this would be equal to sinc of, yeah, again, be, don't confuse with this sinc versus the sinc we have done. Our definition was sine of pi x by pi x is sinc of x. This derivative, this definition is sinc of pi x, that you same thing you write it as sinc of pi kx. Okay, so be clear with that change of notation that happened from the borrowed slides here. But I these things are good, I don't want to do it myself. All these things would take a while. So if you look at it in terms of images you plot it, that's how it looks like. And if you want to know sinks in both x and y, you are multiplying them together, right? So that's how it would look like. And this is again a more generalization of what you have seen, the Gaussian function, 2D Gaussian function. So if you want to get the same thing there, suppose I could have written it as minus of r by sigma whole square, r by root 2 sigma whole square. If you write it, it's my e power minus x square, you would get it. Okay, then you, if you do the change of variable, then you would see you would derive at the same expression here. So this again I want you to derive yourself now that we have done a one important special case of it. So this I leave it to you again. So look at simply the answer. I'm more interested on how the behavior of in the new, in the denominator you had 2 sigma square, and that 2 sigma square would now come into the numerator. Now look at what is the variance of this Gaussian. So the variance got inversed here, right? That's what is happening there. So what does that mean? If you have a very relatively this is how, if it has a small variance, relatively the variance would become more here, right? Other than that, still it will be a Gaussian. Another observation you could make here is it's a radially symmetric function, and of course the resulting one is also a radially symmetric function, for the simple reason that a 1D so if you make change of variables for a radially symmetric function, it's a, you could write it as a 1D function. So for that, whatever you get should also be a 1D function. By that logic also, you could say that this is radially this has to be radially symmetric. It cannot have a varying in 2D, because 1D Fourier transform of a 1D signal should be again a 1D signal. Is everybody able to follow that? Okay, so this is another interesting function, which is a circular disk function. Now, unlike the rect function, here over a radius, you have this r less than or equal to a, again generalized it to a here. Okay, and this is what again you could notice, this again is a radially symmetric function, correct? So you should be also getting a radially symmetric function here, right? So that's what you would be getting. And this is something you could think of it as an equivalent. If you take any line here, this is equivalent to a 2D sinc function. So not sinc of x into sinc of y, but this is more an equivalent one. But this derivation of this is a little bit more complicated. You have to, yeah, you, I mean, it's a good to try, give it a try, although it's not compulsory for you. You give it a try, and unless you know Bessel functions, that's where you would be getting stuck there, or at least I got stuck there. And then you would see that this is essentially the representation of a Bessel's function. So you need to know a bit of Bessel function here to see what is the Fourier transform of this radially symmetric functions. Yeah, radially symmetric functions are very important functions, particularly in 2D. These are, yeah, of course, radially symmetric we are calling because it is 2D anyways. Okay, this is the Bessel function you would get. You just it's enough to know, minimal thing you should know is this is something you have, it's equivalent to a 2D sink. That's the kind of effect you have it here. And after that, I leave it to you whether you would like to know it also. That would be good, particularly in Fourier optics. If you are going to work where they have point spread functions which are very similar to this, and then you should be knowing this. All these are things becomes very critical if you are doing some optics based Fourier transforms and other stuff also there. Experimentally it is very important. Okay, so then what, this is anyway delta of x comma y. This you already know it, right? For 1 it is delta, so for delta you get 1. Okay, this is what it is there. This, in whichever direction it is, you could already say that this orientation you just if they are symmetric around the horizon, okay, and then you just take a line, that's the orientation you have the change. So that's basically a sinusoidally varying function in the ky, correct? So that's why they are using v here, but that's for us ky here, right? So then, yeah, this is already. So by the way, you, although we are, all the equations are here in terms of integrals, keep it in mind again, as I mentioned, you think of them as summations, and you, in fact, at the end you have only a finite number of frequencies. So this makes a more meaning. This is in fact pretty meaningful the moment you are discretizing, having summations here and having a set of frequencies here. That's what is going to happen the moment you are computing DFT. So you could think of that you are it as, you have an f of xy, you are going to reconstruct that with the help of giving different weightages to the functions for which the frequencies are varying both in x and y. You take all the combinations because here there is one summation from let's say minus n by 2 to a minus m by 2 to m by 2, or 0 to m minus 1, or 0 to n minus 1 here, right? So for each one kx equal to 0, for example, you take all possible variations here, ky equal to 0, then ky equal to some other value, so on and so forth up to 2 pi, right? And all these combinations you are going to, by giving different weights and combining them all together. And of course this is as far as real part, and imaginary part is also there, because you have e power j pi here. And then anyway this also becoming being complex number, and that being once this is real, that would be anyway symmetric, complex conjugate effect will be there for f of uv, and by combining them you could either have the effect of just sine or cosine there, in fact. Okay, this is how you would be, this is how this is the intuition that you should have on how you are reconstructing the image. Okay, so far clear? Any questions so far before I go into this example? Okay, now this is the image given now. Okay, and then there should be absolute magnitude here. This is the magnitude spectrum. You would do all your experiments, magnitude spectrum turns out to be the most important thing. So this is the magnitude spectrum. Now you want to see how a low pass filtered image would look like for this. So what is done here is you take a circle here, you retain only those frequencies here, and the rest you make it to 0. So this is your frequency spectrum. Now from here to here you have come. Now to this, if you compute now again, although the low pass filtering region has been selected, or it is shown here in magnitude spectrum, you would be using both magnitude and phase, in fact. Okay, so you still retain the magnitude and phase values for all these points. The rest you make magnitude and phase 0 only, right? So then to this, if you compute the inverse DFT, okay, now I use the word explicitly DFT now, which I haven't used in the recorded lecture because that discussion haven't happened there. I was just referring to it as Fourier transform. Okay, now if you take inverse DFT of it, this is what you would be getting. So the content, basic content of that information is mainly there here. And you need higher order frequencies basically to construct the sudden edges that are going to be there in a 1D signal. Also you have seen it. Suppose if you have a simple rectangular wave, and if you keep on increasing the frequencies, you would realize that the higher order frequencies would essentially contribute to constructing the edge there, is it not? So in similar lines, suppose if I just keep higher order frequencies here, you would realize that that would give you more of a edges information here. Is that clear? So this would be giving you, it is also having an impact similar to smoothing, because smoothing is a Gaussian filter. If you are applying it, what would happen? A Gaussian filter would, now you imagine it Gaussian rotated here, because that's a 2D Gaussian. Okay, the rest outside that Gaussian, the frequencies would become zero, of course. So with just additional weight would be there, but this is what you would be getting. So equivalent to, in a way, applying a Gaussian here. It's not a Gaussian, in fact it's a proper rect you are applying here, and this is what you get as a as you could rightly guess here, this is smoothed version of it. And high pass filtering, if you are doing, that's essentially equivalent to the edges are there, information related to construction of edges are there in the high frequency. So that's what you would be getting here. So that's at the edges you have the maximum thing here. Is this fine? Then another one here. So you could see here, there is a periodicity of an object is there, even if you look at in the direction of X or in the direction of Y. So this periodicity also, I could see some periodicity here to here, as well as here to here, here to here. In that direction also I could see the periodicity. That's why it would result in higher order harmonics both in X and Y directions. Had this image be in this slightly rotated, these also would have come in a rotated direction, this frequency spectrum. Okay, so that you could say here higher order, if you have periodicity here, that would result in higher order harmonics also here with a similar periodicity. So this is an application of that fact that this has been taken on a paper which has a kind of grid like structure. Thumb impression is taken on that, this being periodic. Okay, and also notice it is not a perfect 0 degrees grid. It's not a grid that is exactly aligned with X and Y axis perhaps. So you could see slight rotation there, and of course the higher order thing would slowly fall down. So what is done here is you should in fact delete maximum values from the frequency spectrum. So you remove the peaks there. So magnitude spectrum, you look at what is the magnitude, you keep a threshold there, and anything below that, above that threshold, you make it to 0, so that that which is contributing to this periodicity, you will get rid of that, and this is what you are left with. And of course there could be some things that are going away in this also while you are doing this, but it's okay. Most of the thing would be retained there. That's how you could remove the background there. Okay, this is another image of the moon. I think this is from lunar orbital images in 1966. Okay, so that because of the rolling shutter speed, they have a limitations on it while capturing the images, so that gave this periodicity, right? And you could clearly see that this being periodic in the Y direction, in Kx Ky you have periodicity here, you just get rid of them and you will get this nice image. So it's very means I'm not very sure how you could do such a nice thing in the time domain. That's very difficult. This periodicity you could nicely exploit in a very simple way in case of a Fourier domain. So that's one very important example illustration that shows you that doing moving into Fourier domain and doing denoising there would make much better sense than applying any simple spatial filter here, because that periodicity would contribute to certain particular frequencies in the frequency domain, and you just mask those frequencies and try to get back, it would give you this nice improved image, denoised image. Okay, So then we talked about this. These are pretty straightforward. You just go through that. And then another important thing is, which you have already seen, but I would like you to also try this out mathematically on when you rotate the object, what would happen to the Fourier domain of it. Of course, you have already seen from the cosine example itself, this orientation would be same as this. So this is a particular periodic sequence, but even for other free things, what you would see is, if you know the Fourier transform DFT for a given image, and if this image is rotated, all its impact will be the Fourier transform also will be rotated. All the required hints for doing this are already here. Applying transformation, this slide and previous slide should be good enough for you to work this out yourself. Okay, so then convolution theorem, since anyway all of you know it, so I'm not going to spend much time. There is no point in again proving all these things. You could do that. So convolution here is equal to multiplication, thanks to that getting rid of the factor of 1 by 2 pi. So here convolution here is also equivalent to multiplication when it comes to the kind of equations that we have considered for Fourier transform and inverse Fourier transform, the synthesis and analysis equations. So how could you exploit that? You have an image, you want to convolve it with a Gaussian in order to get a smooth image before you do the rest of the operations. Multiplication is at any given point of time is less expensive than convolution, right? You all figure it out what would be the order of things. I leave it to you. If I give you n by n, we discussed it multiple times already, earlier lectures we discussed it, so you should be able to say computational complexity of that also. So what you would do is, instead of doing convolution, and the DFT operations are implemented very efficiently, so you would, rather than doing convolution in the time spatial domain, you would prefer going into the Fourier domain, do the multiplication there, and then come back. So what's your assumption? And a genuine assumption is that going back and forth of spatial domain and frequency domain are less expensive than performing a convolution. So this is what exactly you could do. One way is you convolve it with a Gaussian. This is what you would be getting. Instead of that, you compute the Fourier transform of it. This Gaussian also, you know the Fourier transform of it, you multiply them both. Okay, now this should not be a surprising thing to you, because this is a Gaussian and all these are zeros. So when you are this is multiplication, so only this part will be there, that too applying some Gaussian weights. So after that, this is what you would be getting here, the rest becoming zero. And then this result, you take an inverse DFT, this is what you would be getting. So yeah, this also you would be doing in yeah, I meant to upload the assignment, programming assignment. I was occupied with something else and it got delayed. I'll do that. This would come after that assignment. I'll give you some such things. I'll give you for the next to next assignment. I'll give you that. Okay. Yeah. So what is, how is it different? Okay, just the way this has been displayed is different here, where you are using intensities to show rather than the surface plots, and this is what you would be getting. Okay, so that's all for this video lecture, this Zoom session. I will move on to the normal mode. Let me stop the recording.